Hello, my name is Luis Orellana, and I'm currently working at CITSEA UPC in Spain as a part of a European Union Horizon 2020 program called InnoDC. Today I'm going to speak about algorithms to identify resonances, and I will show some results from a tool I'm developing at UPC. First, I will present what resonances are and the oscillatory phenomena related to the connection of VSEs to the network. I will introduce some basic concepts to identify resonances, and I will show an example of VSE connected to an offshore AC network. What are resonances? It's the phenomena when a periodical external force makes a system to oscillate at a specific frequency, as it can be seen in the animation. The oscillation is equal or close to the natural frequency of the system. As you all know, VSEs are widely used to connect large-sized renewable energy power plants through long distances. VSEs represent these external forces of the conventional AC network and interact in a wide range of frequencies, causing oscillations and can lead to instabilities. What can we do to study these phenomena? For this, it's important to come with dynamic models to study these interactions. How do we model the dynamics of VSEs and AC grids? In the literature, is commonly used state space and impedance-based modeling techniques. State space modeling uses a set of linear equations in the time domain as the one in the figure, which models the dynamics of the controller of the converter on one side and the components of the AC grid on the other side. The end result is a state space matrix with a set of inputs and outputs. Impedance-based modeling characterizes the dynamic of the converter as an impedance and connects it at a specified bus of the network. This can be done by using the admittance matrix as it is done for power flow calculations. The result is a matrix in the S-domain where each of its elements is a transfer function. Because it is an admittance, the inputs are the bus voltages and the output is the current coming out of the buses. This section is about the concept to identify resonances. We will use a MATLAB script to show it. The script will be uploaded with the presentation. The example is a vector 1001, which is the red arrow. This vector will go through a rotation matrix and a scale matrix, which is represented by the matrix A. The result is the U vector, which is -2, 0, 2, which is the blue arrow in the figure. How we identify the change in magnitude by looking at the transformation matrix? One way to do it is by looking at the eigenvalues of the matrix. The A matrix can be decomposed in eigenvalues and eigenvectors. The eigenvalues give us an idea about the magnitude, and the eigenvectors about the direction. For this presentation, we will only focus on the magnitude. The product of the left or right eigenvector by the A matrix should be equal to the product of the eigenvalues with its corresponding eigenvector. Eigenvalues can be complex and negative, which it is useful at the time of assessing the stability of a system. For example, a system is unstable when it contains eigenvalues with positive real part. We will use the script to get the eigenvalues and eigenvectors of the matrix A. It can be seen that the eigenvalues in this case with letter D are equal to 2, which is the magnitude we set up in previous slide. We can also see that the product of the A matrix with the eigenvector is equal to the eigenvalues by its eigenvector. And we can see the same thing with the left eigenvectors. The analysis is different when we are talking about transfer functions. A transfer function is composed by poles and zeros. The zeros are the roots of the numerator and the poles are the roots of the denominator. Poles and zeros can be complex and negative as the eigenvalues. The change in magnitude can be seen by looking at the poles. The denominator should be equal or higher in order than the numerator for the transfer function to be proper. Once again, we will use the MATLAB script to calculate the roots of the denominator of the transfer function, which performs the 180 degrees rotation and the change of a scale of 2. The results show that the value of the poles is equal to 2 as it was predicted by the eigenvalues in the previous slides. What should be considered at the time of making the analysis in the frequency domain? Transfer functions which are in the S-domain can be transformed in the frequency domain by replacing S by j omega. J omega is an array of the range of frequencies we want to study starting in omega 1 to omega n. State space matrices can also be converted to transfer functions by using this formula. Once converted, S can be replaced by j omega. The result is an array of matrices, one for each frequency. Finally, we can apply eigenvalues over each of these matrices to identify the change in magnitude for each frequency. How can we identify resonances in a system? To demonstrate this, we will use a second-order transfer function, which is the order of the denominator, where omega n is the natural frequency and c is the damping ratio of the system. The topology of the poles has been classified according to the damping ratio. These categories are overdamped, critically damped, underdamped, and undamped. In this presentation, we will focus on underdamped systems. First, we need to find the roots of the denominator. Second, we need to find a change in magnitude at certain frequency, which is a peak in the frequency domain. A peak is a local maximum, and its location can be found by equal to 0 the derivative of the magnitude of the transfer function. The result is the location of the resonances, which is represented by omega r. Omega r is in terms of the natural frequency and the damping ratio of the system. We have used the second order function of previous slides with a specified natural frequency and vary the damping ratio of the system with a MATLAB script. We have performed the step response of the system and we start seeing oscillations when the damping ratio is lower than 0.707. We can see this by looking at the step response plot in the time domain and the poles. The poles are complex conjugate for each damping ratio. They are located closer to the horizontal axis when they are closer to 1. The value of 0.707 is what it is stated in the literature. We have created two examples to illustrate this concept. First, we will use an RLC circuit fed by a voltage source. These are the dynamics of this electric circuit in the S-domain. The ratio between the current and voltage, which is the admittance, show a high-order denominator, which is what we are looking for. We find the denominator roots, and we can see that the damping of the system is lower than 0.707. Therefore, it is expected to see a peak in the frequency domain by plotting the magnitude of the admittance. In the plot, it can be noticed that the resonance is close to 1000 Hz. The second example is an RLC circuit in parallel fed by a current source. Once more, the dynamic equations of the system in the S-domain are expressed. In this case, the ratio of voltage and current, which is the impedance, show a higher order denominator. We look for the roots of the denominator, and the damping of the system shows the system is lower than 0.707 as previous case. So we transform the impedance from the S-domain to the frequency domain, and we can see in the plot that there is a resonance close to 1000 Hz. It is time to apply all these concepts in a larger network. This network could represent part of a string in an offshore wind farm. The system has 3 VDCs connected. So, for these 3 models were developed, one nonlinear Simulink model and 2 linear models in the QD reference frame. One is the admittance matrix model and the other one is the state space model. The admittance matrix model has 7 nodes which make a 14 by 14 matrix, and the state space model has 64 states. So now let's see how the tool developed performs to identify resonances. It is worth saying that the time of the simulations have been edited for this presentation video. Once the tool is loaded to MATLAB, the first step is to symbolic model the converter and the AC network. The tool models the admittance and the state space matrix. We run the model. We choose option number 1, modeling. The tool asks for the number of converters connected to the network, in this case 3. It also asks for the type of network we want to work with. The example is number 3 in this case. The second step is to linearize both linear models. We need to run the nonlinear Simulink model in order to obtain the steady state values, so they can be replaced with other input parameters in the linear symbolic models developed in step 1. During this step, the admittance matrix symbolic model is converted to transfer function and the state space symbolic model is converted to a state space matrix. In this case, we choose option number 2, linearization. And we just want to run one study case. The third step is to check how closely the dynamics of the linear state space model reproduces the nonlinear Simulink model. The tool performs a step in active power to see this. In this case, we choose option 3, plot. Here we can see the step in active power. The gray line is the nonlinear Simulink model and the red line is the state space model. Here we can see the current and voltage in the D reference. The results show that the state space model reproduces closely the dynamic of the nonlinear model. Therefore, we can continue with the process. The fourth step is the analysis section. In this section, the tool performs what we have seen so far, which are eigenvalues, poles and zeros in the S domain, and eigenvalues in the frequency domain. So, we choose option number 4, analysis. The plots show that the state space and admittance matrix models are similar because eigenvalues and zeros match. Now models are validated and we can continue with the analysis. In the frequency domain, it can be noticed several resonances in the system, and every eigenvalue in the frequency domain. Because the matrix was 14 by 14, there are 14 eigenvalues. The resonances are located below 100 Hz, around 500 Hz, 1200 Hz, 1500 Hz. So it is worth saying that it is easier to spot the resonances in the frequency domain than looking for poles or eigenvalues in the S domain. The presentation has come to an end, and these are the conclusions. Along the presentation, it has been presented algorithms used in the literature to identify resonances, which are based in detecting the change in magnitude of the inputs at the time they go through the system. The presentation shows the importance of the damping of the system by indicating whether or not the resonance oscillatory phenomena will be present in the system and identified by time domain or frequency domain plots. The resonances exist for a value of damping lower than 0.707. Finally, it has been shown that S-domain and frequency domain tools are very helpful at the time of detecting resonances of large systems. The time to introduce all these topics was limited, and I hope the presentation provides a useful guide. If you have questions about the topic and the tool, you can get in contact with me at this email or look at the reports available on the website of the InOdyssey project. Thank you.